So today I'm going to tell you about radial stability of spherical bosonic stars and critical points. And this is a work that we've done recently in collaboration with Nuno Santos and Carlos Herdeiro. And this was accepted for publication in JCAP. So Professor Carlos already told us yesterday about the wonderful world of compact objects with bosonic fields in general relativity, so I'm not going to tell much about that. I think we are all well motivated to study this kind of solutions. But I'm just going to say that for this exotic kind of compact objects, some of them do not have a clear formation mechanism. But this is not the case for this type of bosonic stars. So the bosonic stars have a clear formation mechanism, which is the gravitational cooling. And we can use this kind of solutions as models for lumps of ultralight dark matter. But okay, if we want to use this kind of solutions as model for existing compact objects, we must address the problem of stability. So we have to study how these behaviors, this kind of solutions behave under some small perturbation. This problem was addressed in various works, so I'm just going to mention a few. So there are these works made in the 80s by Glaser and Yetzer, where they consider the radial stability of bosonic stars. And they show that we can, when we look for the behavior of the solutions in terms of the central value of the field, then we can separate these solutions in radially stable and radially unstable solutions. There is another work in the 90s by Seidel and Swen, where they address the linear and nonlinear stability of radial stability of this solution for mini boson stars in this case. And they show that if we take a solution for the stable branch and we perturb radially this solution, then we have some radiation emission. The solution loses mass and moves to another solution of the stable branch. But if we perturb a solution in the unstable branch, then the solutions either decays to a black hole or it moves to a solution in the stable branch. And there are also another work, more recent work, where they address this radial stability for Proca stars. But they study in particular the frequency close to the maximum value permitted for the mass. Okay, so in our work we consider both the scalar solutions and the Proca solutions. For the scalar solutions, we consider three different types of potentials. We consider the potential for mini boson stars, and we also consider two potentials with self-interaction, which is the one for solitonic solution, which is this one, and this V0 is the degenerate vacuum of the solitonic potential. And we also consider an axionic potential, where this Fa is the PC-Queen symmetry breaking scale. And we consider this potential for the Proca field. Okay, so when we consider these different potentials in our Einstein equation, we have to solve the Einstein equation subject to these two energy momentum, and we have this field equation. So for the scalar field and for the Proca field. Okay, so first, in order to find the perturbed equations, we first find the equilibrium solutions, And for this, we are going to consider a spherically symmetric static spacetime. So we consider this form for the line element. So the line element is static, but for the fields, we consider this harmonic time dependence. And for the perturbed solution, since we are going to study this radial stability, we consider this form of perturbations. And so we consider this form of perturbation for the metric, and this for the fields. And here we see how these functions are all defined. So these perturbations, the perturbation depends on a perturbation frequency, which we call capital omega. And when we assume these kind of perturbations in our equations, then we find some other sets of equations that we have to solve in order to find these perturbation frequencies. And these equations that we are left with, they all depend on this capital omega square. So they depend only on the square of the perturbation frequency. So if this omega square is positive, then our solution is stable. If it's negative, then the solution is going to be unstable. We can have an infinite number of perturbed frequencies, and these perturbed frequencies are labeled by the n, which is the node number. The smaller possible value for the frequency is going to be the fundamental state, and all other, for n different than 0, then we have the excited modes. So since the perturbation, the fundamental mode has the smaller possible frequency, then if this mode is stable, then all other modes are also going to be stable. If this fundamental mode is unstable, then the first excited mode can be either stable or unstable. So the fundamental mode is going to be the more interesting case for us to look, since we are studying radial instability. But we also obtain the solutions for the first excited modes that we use to compare with some known results from the literature, but which I'm not going to show here. Okay, so for the boundary conditions, basically we consider expansions at the center of the star and at infinity. And at the center of star, we want our solutions to be well behaved, so we impose smoothness there. And at infinity, we impose asymptotic flatness. So this is kind of a summary of how our functions behave at these two regions. Okay, so what we do is we solve our equations subject to those boundary conditions that are mentioned in order to find the perturbation frequencies. But we can also address the stability of a solution by using the critical point method. So in this kind of method, we look to a plot of the mass in terms of the value of the field at the center of the star. And we have some critical points. So here a maximum and here a minimum. And these critical points, they are related to changes in the stability of our solution. So okay, we have some critical points. And now, in order to see if that really is, if there really is a change in stability in that point, we have to look for this, for the radius of the star in terms of the field at the center of the star. So for an even mode, if this derivative is negative, then we have a change in the stability. But for an odd mode, if this derivative is positive, then we also have a change in the stability. Otherwise, this point will not correspond to a change in the stability. So here in this example, the first point, so this point here, which is the maximum of this function, indeed corresponds to a change in stability. but this second point does not correspond to a change in stability. So here we have the results for the mini boson star. So here we have the parameter space in terms of the value of the field at the center of our star. Here we see that as for neutral stars, we also have a maximum value for the mass of this star. And here we have two critical points. So for this, just to mention, this is the mass and this is the binding energy. So for this point, for this maximum point for the mass, we have here a negative value for the binding energy. But for this minimum value of the mass, the binding energy is positive. Okay, so we also can see that our solution of the our metric function is well behaved as as imposed by the boundary condition. And I guess this is it for this model. So this is for mini boson stars. When we consider self-interactions, then the picture can change quite a bit. But this will depend on the parameter that we set for these self-interactions. So for in this case, when we consider this V0 equal to 0.2, then we can have here a solution where we have various critical points here in this plot for the mass. And we will see that this indeed corresponds to, we will have in this case, 2 stable branches and 2 unstable branches. But I'll talk a little bit more about this in an instant. So here we see that this point 3 and this point 5 correspond to negative binding energy. Another thing that I don't know if you can see it well here, but in this case, you can also have an inversion of the position of a change in the position of this maximum possible value for the mass. So for the mini boson star, we only have one point corresponding to a global maximum. In this case, we can have a global and local maximum for the mass. And in this case, this 0.5, it has a higher value, corresponds to a higher value of the mass than this 0.3 here. So here's the case for the axion boson star. So in this case, we can also have multiple critical points in this plot. We can also have this kind of inversion that I mentioned in the case for the solitonic boson star, but this is not displayed here. So in this case, we also have the 0.6 and 0.8 corresponding to a negative value for the binding energy, while these points 7 and 9 have a positive value for the binding energy. This is the case for the Proca star, so it's similar to what we have for mini boson stars. So we have also here a maximum value for the mass, which is significantly larger than the case for the mini boson stars. So here it's close to 1, while for the case of the mini boson star, it was around 0.6. We can also look for this plot of the mass in terms of the radius of the star. Okay. So in this, on the left side, we look for this mass over radius, while on this right side, it's here we plot the compactness in terms of the central value of the field. Okay, so we see that for configurations with self-interactions, we can have solutions with smaller radius and more compact than in the case of mini boson stars. Again, the case for the Proca star is similar to what we have in the case of mini boson stars. Although in this case, we can also have solutions that are more massive and more compact than in the case of the mini boson stars. Okay, so here we are looking, now we are looking for this. Here is the frequency at the center, the perturbation frequency squared. And this is for the mini boson stars in the center for the solitonic boson star, and in the right for the axionic boson star. And here, this is a log plot. So here we have this behavior of the frequency increasing with the central value of the potential. Then it drops to 0. And when it drops to 0, these signs are change in the stability. So when this squared frequency is positive, the solution is stable. If it's negative, the solution is unstable. So when the frequency is 0, then we have this marks a change in the stability of the solution. So this all that's plotted here is for the fundamental mode. So in this case, we have this behavior. The frequency increases with the central potential, with the central value of the field. Then it drops to 0 at this point. And then it becomes negative. So this first point corresponds to the maximum value of the mass. So here we indeed have a change in the stability. But this other point that corresponds to that minimum in the mass over central value of the field, we don't have a zero mode. So we don't have any change in the stability of the solution. When we look for the self-interaction case, so for the solitonic and axionic case, then we see that we have multiple zero modes. So we have changes in the stability. So here we have this colored region corresponds to the stable branches, and this white regions we have the unstable branches. The same here for the axionic case. In this case, for the axionic case, we see that this point that corresponds to a critical point, it's not, it does not correspond to a change in the stability. So for the Proca star, again, we have something that's similar to what we have in the case of mini boson star. So we have only a change in the stability here. So here is a stable branch, and after this point, we have the unstable branch. And here we also have a point that does not correspond to a change in the stability. Okay, so we also, so as we have seen, if we have a critical point in the mass over central value of the field, then this is related to a change in the stability, but does not necessarily means that we have this change in the stability. In order for us to have this change, this point has to correspond to a zero mode, so a point where the frequency goes to 0. And we see that for some of the critical points, this is not true. And this is corroborated by the critical point method. So these 2, 9, and 11 points, they are not zero modes. So we do not have change in the stability, while all the other points correspond to changes in the stability. Okay, so I'm moving on now to my final remarks. I think I was on time. So Here we consider the solutions for mini boson stars and also for some solutions with self-interactions of the scalar field, and we also considered Procca field. And we see that self-interactions leads to a more complex parameter space. In particular, we can have multiple critical points in our mass over central value of the field for this kind of solutions. And for the spherically symmetric Procca stars, there are works, Professor Carlos Herdeiro mentioned them yesterday also, that but they show that the spherical solution is not the real stable, the real fundamental state for the Procca star. So if we perturb the solutions, they move to a prolate Procca star, not for a spherical Procca star. So this stable branch that we've seen is not dynamically stable. Okay, so the system will not evolve to the spherical Procca star, it will evolve to something else, in this case for a prolate Procca star. And just to emphasize that this derivative, so these critical points, is not a sufficient condition for the existence of a zero frequency mode, so we have to be a bit careful when we are doing this kind of analysis of the stability. Okay, so thank you.
Congratulations for the presentation. I have a curiosity. Is there a special motivation for the values that you use? For example, V0 equal 0.2? If not, why do you use that value?
Thank you. So those particular values that we chose for the V0 and FA, we chose them because we have a significant difference in this case than for the mini boson star. Because depending on the parameter we choose, we can have a situation that's very similar to a mini boson star. So we wanted to study these other cases where we have these differences to analyze these changes in the profile of the solution.
Yeah, thank you for the talk. So it's not directly related, but you mentioned at the beginning that the formation mechanism is known for some and not for others or something, and if you could comment on that, and also what is gravitational cooling? That's my question.
Sorry, I don't know much about that. So, okay. Yeah, because there are some exotic compact objects, but they are as close to a black hole, but you have like a very small distance between the horizon and the radius of the star. So these are black hole mimickers, so we can have a lot of interesting results from this type of solutions, but we don't have any clear formation mechanism, so we don't know exactly how we could form such compact object. But I don't know much about this gravitational cooling, sorry.